Hello, Rockstars. Today we will be addressing a very important topic on mechanics, Newton's law of motion. So, in the class today, we will be splitting the lesson into three different sections. In the first section, we will be talking about the concept of mechanics, under which we will be addressing the Newton laws of motion, the weight of a body in a lift, the law of conservation of linear momentum, and secondly, we will be listing the formulas in mechanics, and lastly, we will be using these formulas to crush UTME questions. Greetings, future rockstars, and welcome to Josh White Academy, where we fuel your success with experience-backed strategies and science-based tutorials. If you are new to this channel, I am your host, Josh White, and it's my mission to help you crush high school with confidence and clarity. So if you are new to the channel, please do well to consider smashing the subscribe button, turn on the notification. Let's get started. So in the previous class on the equations of motion, we talked about motion but did not address the cause of motion. You see, for a body to move, there must be a cause. And the study of motion and the cause of that motion is termed mechanics. Mechanics is a branch of physics that deals with the study of force and how it influences or causes motion. Now, this concept was studied and brought up by Galileo Galilei, and after his death, this work was advanced by Isaac Newton, through which he postulated the three laws of motion. So now, the first Newton's law of motion. Newton's first law of motion states that a body, if at rest, will remain in the state of rest, or if it is in motion, will continue in uniform motion unless being encountered or influenced by an external force. What this simply means is that a body that is at rest will remain in that same position. For instance, this marker in my hand will remain in this position forever unless there is an external force that will cause it to change position. Or if a body is in uniform motion, that body is meant to continue in that uniform motion unless there is an influence of an external force. Now, imagine someone inside a vehicle that is moving. If there is a sudden application of brake, you will notice the passengers will jack forward, seeming to continue in that forward motion, which explains Newton's first law of motion. Now, this law is also known as the law of inertia. Inertia simply means the reluctance is the tendency of a body to remain at rest or to continue in uniform motion. Now, Newton's second law of motion. Newton's second law of motion states that the rate of change of momentum is directly proportional to the applied force and moves in the direction of the force. Now, it means that force is directly proportional to the rate. Remember, I say rate is always divided by time. is directly proportional to the rate of change of momentum. That momentum is actually the product of mass. Momentum is actually the product of mass and velocity. So, Newton's second law of motion states that the force is directly proportional to the rate of change of momentum. The change of momentum is from the mv to the mu, final velocity, initial velocity. So from here, remember whenever we remove our variation sign, we always add a constant. But in the case of this, our constant is 1. That means it will still give us our mv minus mu all over c. If we cross multiply, this will become ft is equals to mv minus mu. mv minus mu, which is the change in momentum, is also known as impulse. So impulse is equals to force multiplied by what? Time. So impulse is the product of force and time, or the change in momentum, the final momentum minus the initial momentum. So Newton's second law of motion tries to explain that if more force is applied, the body tends to have a more momentum. That means there is a direct relationship. That means there is a direct relationship between the rate of change of momentum and the applied force. Now, I would like you to take note that momentum of a body is related to mass and velocity, as this formula explains. So, a big body with a little velocity can have similar momentum with a small body with high velocity. Let's say, for instance, a body has a mass of, let's say, 100 grams and moves with a velocity of 10 meters per second. Our momentum, which is mass and velocity, will be equals to 1000 gram-meter per second. So, whereas a body that has a smaller mass, let's say the mass is 1 gram, but moves with a very high velocity, let's say 1000 meters per second, will have the same momentum as what? 1000 gram-meter per second. So the impact from a bullet with 100 grams shot with a velocity of 10 will be the same with a bullet of 1 gram shot with a velocity of 1000 meters per second. That is momentum. Now, and lastly, Newton's third law of motion, the easiest among all, it states that for every action, there is equal and opposite reaction. In another word, it means that action and reaction are equal and opposite. Now, the ability for me to stand here, the action of my weight on the ground is pointing downward. My weight is pointing downward. The reaction of the earth is pointing upward. So, it's able to hold me. So, I'm not going up, neither am I going down. So, the weight, my weight, and the reaction of the earth are equal in magnitude and opposite in direction. Now, someone who is swimming and he is paddling the water backward, as he paddles the water backward, he is propelled forward. So, the action of him paddling the water backward the water in reaction propels him forward. Similar to someone who is paddling a canoe. As he paddles the water backward, the canoe propels forward. Similar to the recoil of a gun. Someone who shoots a gun, the backward pull on the gun, which is the recoil force, is equal but in opposite direction to the propelled bullet. Similar to a rocket, similar to a jet. So, for every action, there is equal magnitude of reaction but opposite in direction. Now, let's talk about the weight of a body in a lift. Now, the weight on a lift. Now, let's imagine a man in an elevator. There are two forces that act on this man. The number one is his weight, which acts downward in line with the gravitational pull. Secondly, is the reaction of the lift, the ground of the lift, sustaining his weight, which acts upward. So, these are the two major forces that act on a person in an elevator. The weight pointing downward and the reaction pointing upward. So, we will be using this to explain 4 different scenarios of an elevator. So you can be able to know how to master it and use it to crush any physics high school or college problems. Now, the first one is when an elevator is at rest or in constant or uniform motion. So, when an elevator is not moving or is moving with a uniform acceleration, we must know that at that point there is no acceleration because our velocity is constant. So our final velocity minus initial velocity will give us a 0. That means our acceleration is what? 0. So in that case, bringing our formula back, our net force is equals to our downward, which is our weight, plus or minus our upward, which is our normal. So always the weight or the apparent weight of the person is actually the normal. So this is our force, which is equals to MA is equals to the weight, which is mg, plus or minus the r. So if we collect like terms, our apparent weight will be equals to mg plus or minus ma. That's m open bracket g plus or minus a. Why I use plus or minus is because the elevator is not moving up or it's not moving down. So it's either plus or minus. So there is no. So now in this case, our a is 0. That's m open bracket g plus or minus 0 will still give you g. So mg. So the apparent weight is mg. It is normal weight. So in the first instance, when an elevator is at rest or constant velocity, its weight does not change. Now, secondly, if the elevator is moving upward, so now take note, if this elevator is moving upward, the dominant force between these two forces is the reaction, because it is going in line with the reaction. So our net force now, which is MA, our net force is MA. So our R is bigger than our weight. So our R minus mg. So in simple, this will give you our R to be M open bracket A plus G. So this person in this moving elevator will experience more weight than his actual weight. So the person will feel heavier than normal if the elevator is what? Moving upward at a particular acceleration. Now, the third scenario is when the elevator is moving downward. So in this case, our elevator is moving downward. So now, what will be our dominant force? Our weight will be our dominant force because it is moving in line with the weight. So in this case, our net force will now be weight minus reaction will give us what? Our net force, which is MA. Remember, our weight is what? mg. This will give us our reaction to be equals to M open bracket G minus A. So in this case, the person will feel lighter than his original weight, as we will see subsequently. So, and in the last scenario, when the elevator falls by free fall, so when the elevator falls under free fall in this sense means that our acceleration is equal to our acceleration due to gravity, because the lift now is falling with an acceleration that equals to the acceleration due to gravity. Now, in this case, there is no reaction. So his weight is going down. There is nothing trying to support him up. So our reaction R is 0. So in this case, his apparent weight, which is R, is what? 0. So we call this in physics, we call it weightlessness. At this point, the person falling under free fall is weightless, because our acceleration equals to our gravity. So it's expedient you master these four scenarios. The first scenario, elevator at rest. At this case, there is no change in his what? Weight. His R is the same as mg, which is his weight. The second occasion is when the elevator is moving upward. So if you are moving upward, your apparent weight will increase. If you are moving downward, the apparent weight will do what? Decrease. So it will be G minus the acceleration. And lastly, when the elevator falls under free fall, in that case, there is no weight at all, because of the reaction is 0, making the body to be weightless. Now, let's talk about the law of conservation of linear momentum. So, the law of conservation of linear momentum was coined from Newton's second law and third law of motion. It actually states that in a system of colliding body, the total momentum is conserved, provided there is no net external force acting on that system. In another way, it states that the total momentum before collision is equal to the total momentum after collision, provided there is no influence by an external force. So, to understand this law, we will have to differentiate between two types of collision: the elastic collision and the inelastic collision. So, a collision is said to be elastic if the momentum and energy are both conserved. That means there is no change in momentum or energy between the before and the after. Whereas in inelastic collision, momentum is conserved, but energy is not conserved, because energy is lost through heat, through sound, or even through elastic potential energy. So, elastic collision, momentum and energy is conserved, mostly the kinetic energy. Whereas in inelastic collision, momentum is conserved, but energy isn't. Now, on elastic collision, back to the law. If two bodies are colliding, the momentum before collision, remember momentum is mass multiplied by velocity. So the momentum before collision of the first body will be m1 u1, mass and velocity. For the second body will be m2 u2. So this is the total momentum before collision. You see it? Then we said it's equal to the total momentum after collision. That's m1 v1 plus m2 v2. So this m1 u1 is and m2 u2 is before collision. Then this one is what? After collision. Our first body, our second body, our first body, our second body. But this is for elastic collision, where the momentum or kinetic energy is what? Conserved. So for kinetic energy, it will be 1/2 m u1 square plus 1/2 m2 u2 square is equals to 1/2 m1 v1 square plus 1/2 m2 u2 square. That is for elastic collision. But most of the time, the kind of collision we experience is inelastic collision. Now, in a perfectly inelastic collision, before collision will be m1 u1 plus m2 u2. The body sticks together and moves with a uniform velocity. So, in this case, our v1 and v2 are the same. So it will give us the formula of equals to m1 plus m2 close bracket v, since they both have the same velocity. So formulas: our momentum is mass multiplied by velocity. Our impulse is the change in momentum mv minus mu, which is m open bracket v minus u. Also, our impulse is the product of force and time. Then we have for elastic collision, m1u1 plus m2u2, momentum before collision is equals to that after collision, m1 v1 plus m2 v2. For elastic collision, then for inelastic collision, m1u1 plus m2u2 is equals to m1 plus m2 v when the both bodies stick after collision. Then we have for when an elevator is moving upward is m open bracket g plus a, and if it is going downward, our apparent weight is m open bracket g minus a. So these are very important formulas. Master them. Now, rockstars, let's use these formulas to go and crush UTME questions. Come with me. So, the first question. The tendency of a body to remain at rest when a force is applied to it is called, we've talked about this before. Our answer is what? Inertia. The tendency of a body to be at rest, or if it is in motion, uniform motion. So to the next question. Calculate the apparent weight loss of a man weighing 70 kg in an elevator moving downward with an acceleration of 1.5 meter per second square. Remember we said if the elevator is moving downward, we are using this formula. So let's write down our data. Our mass is 70 kg. Our acceleration is 1.5 meter per second square. Our acceleration due to gravity is 10 meter per second square. So our apparent weight is m open bracket g minus a. So our m is 70, our g is 10, our a is 1.5. So 70 multiplied by 10 minus 1.5 will give you 8.5. So 70 multiplied by 8.5 will give us an apparent weight of 595 Newton. So our answer is what? B. To the next question. When an X-ray collides elastically with a free electron, there is a conservation of, remember when we talked about our elastic and inelastic collision, we said that in elastic collision, both momentum and energy are conserved. But for inelastic collision, only momentum is conserved, whereas energy is not. It is decreased. So that means our answer is what? Both momentum and what? Energy are conserved in elastic collision. To the next question. A ball of mass 5 kg hits a smooth wall normally with a speed of 2 meters per second. Determine the magnitude of the resulting impulse. So recall from our second Newton law of motion, our impulse is our change in momentum. So let's write down our data. Our mass is 5 kg. Our initial is 2 meters per second. So they are asking us to find our impulse. So our formula, our impulse is m open bracket v minus u. But now I want to take note. When you throw a ball to the wall, they use the word smooth wall so that we can see that an elastic collision. You throw a ball to the wall. The ball hits the wall and bounces back to you. So that means they are of equal magnitude. If there is no loss in momentum and energy, it is in equal magnitude but in opposite direction. So that means our U we'll take a negative mark because it is moving in opposite direction to the final velocity. So in this case, our mass is 5, our velocity will be 2, then our initial velocity, there is a minus here, -2. So please always take note. And many students fail it at this junction because they don't understand that the body is moving in opposite direction. So in this case, our minus will give us a plus. 2 plus 2 will give us a 4. So 5 multiplied by 4 will give us an impulse of what? 20 kilogram meter per second. So our answer is what? A. To the next question. A body of mass 12 kg traveling at 4.2 meter per second collides with a second body of mass 18 kg at rest. Calculate their common velocity if the two bodies coalesce after collision. JAMB likes questions like this a lot. So please stay focused. Let's write down our data. Our first mass is 12 kg traveling with a velocity of 4. Our U1 is 4.2 meter per second. A second body of mass, our M2 is 18 kg at rest, meaning our U2 is what? 0 meter per second. Calculate their common velocity if the two bodies coalesce after collision. We are finding our V. Remember, that was exactly what we stated here. Where two bodies undergo perfectly or complete inelastic collision by sticking together and having similar velocity. So now let's write our formula. M1U1 plus M2U2 is equals to M1 plus M2V. So our M1, 12 times U1, 4.2 plus M2, 10 times 0 will surely give us a 0. Is equals to M1 plus M2, that's 12 plus 18. Close bracket, our V is what we are looking for. You see it? So 12 times 4.2, 50.4 is equals to 12 plus 18 will give you 30V. Divide both by the coefficient of V. So our V, 50.4 divided by 30 will give you 1.68, which is approximately 1.7 meter per second. So our answer is what? D. Very important. Please master this kind of question. JAMB likes it a lot. Now let's take the last question. When taking a penalty kick, a footballer applies a force of 30 newtons for a period of 0.05 seconds. If the mass of the ball is 0.075 kilograms, calculate the speed with which the ball moves off. Let's write down our data. Our force is 30 newtons. Our time is 0.05 seconds. Our mass is 0.075 kilograms. Calculate the speed at which the ball moves up. We are finding our velocity, our final velocity. So this looks like Newton's second law of motion, which is F is equals to M open bracket V minus U close bracket T. So our force is 30 is equals to our mass is 0.075. Our final velocity is what we are looking for. Our initial velocity, the ball is at rest before it takes the kick. So it's 0 all over. Our time, which is 0.05. So cross multiply, this will give us 1.5 is equals to 0.075 V. This times V. So divide both sides by the coefficient of V. So 1.5 divided by 0.075 will give you a 20 meter per second, which is what? 6. So future rockstars, this is all basically you need to know to crush your dynamics in your JAMB. So if you gain something from this video, please do well to smash the subscribe button, turn on the notification, like, share, comment, and in the next video we will be talking about expansivity, the expansion of solids. You can't afford to miss that class. I remain your host, Josh White, living to catch you another day. Shalom.